Thank you very much for inviting me here, and I'm glad to share my recent work. So I will first start with an introduction to data assimilation, just to provide you with some background. Then I will try to cover these three topics, bridging idealized and operational models, conditional Gaussian Koopman network, and assimilative causal inference. So these three topics may sound like separated, but actually they have tight connections. So first, this bridging model will provide us a lot of this high-quality, high-resolution dataset, and this dataset will help us build new digital systems. And these digital systems will help us do efficient data assimilation and uncertainty quantification. Then about this causal inference, they will help us to understand these what-if scenarios. And actually, this is also an important question for these digital twins. And the assimilative causal inference will also help us to answer these attribution and predictability questions, and will help us to solve these tipping points, extreme events. And all these topics will be very helpful to build these new bridging models. So I'll try to emphasize each point one by one, but I also try to provide the links between these different aspects. So first, a quick introduction to data assimilation. So what is data assimilation? So data assimilation seeks to optimally combine a numerical model with observations to improve data assimilation results. So why should we do data assimilation? Because the model is typically very chaotic and has uncertainties, while the observations are not perfect as well because they contain noise and they are often available only for a subset of state variables. So basically we have two things, and neither of them is perfect, but we try to combine them to make results much better. So historically, data assimilation was developed in the field of numerical weather prediction, and these systems are highly chaotic, where future states are very sensitive to the initial conditions, and this is known as the butterfly effect. And therefore, an accurate initialization is extremely important for the skillful forecast. So here I show a very simple example, which is this Lorentz 63 model. It is a nonlinear model, but it's only like three-dimensional system. So from the figure here, you can see this blue curve is just one realization from the system, and this is for the x variable. And you can also see this red curve, which is almost the same as this blue curve from beginning, but I try to perturb the initial condition by only 0.1%. So you can see at the beginning, these two curves, they almost overlap each other, but at a certain point, maybe around time 20 or 15, they start to diverge. And in the second panel here, you can see the error between these two curves. And in the y-axis, actually I use a log scale. So you can see from maybe 12 to 20, this linear increase of the error, but because I use the log scale in y-axis, the error growth actually is exponential, right? So this tells us if we have some small perturbation at the beginning, then for these chaotic systems, this error can be amplified significantly afterwards, which also means, we have to make sure we have good initial condition to guarantee a relatively long range forecast. So of course, initialization does not just mean we try to denoise. It will also help us do many other things. So for example, usually in practice, we only have these sparse observations, like we have observations at a few grid points. But in order to run a high-resolution model, we have to make sure our initial condition covers everything. So basically, we'll have to use data assimilation to do some interpolation to get the initial condition at every grid point from large scale to small scale. And similarly, for some systems, maybe we'll only have these partial observations. For example, for the ocean, we may get good observations at the surface, but we have no observations for the deep ocean. But when we run this entire model, we have to know the state for both the surface and the deep ocean. So we have to use data assimilation and observations from the surface to recover the state in the deep ocean. Then we can run the entire system to do the forecast. So of course, nowadays, data assimilation is very useful for many other tasks like this sequential data assimilation, parameter estimation, the post-processing of data, and uncertainty quantification. So Mathematically, this data assimilation is quite simple and straightforward. Let's say we have the state variable, we use U to represent it, and we also have this partial and noisy observation, we use this V to represent it. So basically, data assimilation provides a statistical state estimate, which means our result will not just be a number, but it will be a distribution. So the underlying principle of this data assimilation is given by this famous Bayesian theorem. So we have this so-called prior distribution, which is a distribution based on our prior knowledge, which can come from a model or come from any knowledge we have. Usually we run our model forward to get a distribution. And the reason it's a distribution because the model is very chaotic and turbulent. So you try to use a distribution to cover all possible range of the state. While this likelihood, it tells us how consistent our observations is with the model. So it's a conditional distribution of this observation given the model state. Their product is called the posterior distribution, and that is a distribution we want to use as a data assimilation solution. So essentially, it's a state estimation of this U, but it is given the observations. So the posterior distribution integrates information from the prior and from the likelihood. Basically, it combines information from the model and observations. But how to incorporate the information depends on the uncertainties in this prior and its likelihood. So I show a very simple figure here. You can see this blue curve, again, it's a prior distribution. And this black one is likelihood. And in this case, they have similar uncertainties here. And therefore, when we have posterior distribution, basically we try to put the posterior in the middle, right? We don't have any biases towards either of them. But in the second case, you can see this prior distribution, which is in green, has a smaller uncertainty than this black curve, which is likelihood. And therefore, we will trust this prior more than the likelihood. So our posterior will be closer to this prior distribution. So depending on when the state estimation and observation incorporation are made, data assimilation can be classified as filtering and smoothing. So filtering uses only the past information to improve the initialization of the real-time forecast. And there are many filtering methods. The most famous one is called Koopman filter. Koopman filter works for the linear and the Gaussian systems, and it has closed analytical formula, so we can easily run these equations without using any numerical method. But of course, in practice, our systems are usually highly nonlinear, highly non-Gaussian, so we have to rely on this ensemble Koopman filter or particle filter to get some numerical approximation. So on the other hand, we also have this method called smoothing. So smoothing estimates the state at a given time by utilizing the observations from both the past and the future. And the main purpose of using this smoothing is to do a post-processing of the data. So it's kind of like interpolation, but you don't use like a linear or quadratic rule to do the interpolation. You use the dynamical information to tell the system how to do the interpolation. So there are many key challenges in this data assimilation, especially for high-dimensional systems. They include like sparse observations, high computational and storage cost, these inherent model errors and sample errors using limited ensemble sizes. So here I show a very quick example of how data assimilation can solve many of the problems I mentioned previously. And this is a work led by my former student, Jeff Covington. So we study this sea ice problem. If you can see this red box, that is called the marginal ice zoom. And you see a lot of these small pieces of ice, which are called the sea ice floe, FLOE. So what we have here is like in June 26 and June 28, we can identify a lot of these sea ice flows. But because of the cloud, we cannot see a lot of these flows in June 27th. But in order to give a complete data set, we have to apply some method to recover the sea ice flows in June 27th. Of course, for the state-of-the-art method, people say, hey, we can use linear interpolation. But then we think for a second if this is a good method or not. The answer is, of course, it's not, right? Because these sea ice flows, they are driven by the ocean field, and ocean has a lot of these eddies, which have this rotation behavior. So if we use a linear interpolation, then you can see we'll miss the actual location of the sea ice flow. So what we do here is we use data assimilation to build this dynamical interpolation framework. So we run our coupled system of atmosphere, ocean, and sea ice forward. Then we use limited observations of these sea ice flows to guide our system. Then this is data assimilation. So what we can get is, because we have this dynamical information, so we can get the right curvature of many of these flows. So the distribution of the curvature, the distribution of the angular displacement are closer to the truth comparing with our empirical forecast model. And in addition, although we can observe the locations of the CS flows, we cannot observe the thickness of the CS flows, right? Because these are just images. But this thickness is very important for the dynamics of CS. So we can augment our coupled system by including the thickness as additional state variables. So we can estimate the thickness here. And lastly, we can also recover the ocean field because we have this coupled system. If we know the trajectory of the flow of the sea ice flow field, we can recover the ocean dynamics and uncertainty as well. So basically, I want to say here, we can use data assimilation to do this interpolation, and we can quantify the uncertainty, and also we can estimate the parameters. So now I'll move on to the main part of my talk. The first topic is about this bridging idealized and operational models. And eventually, we want to build an explainable AI framework for Earth system emulators. So why did we want to do this work? Because in reality, we have different models. We can roughly classify our models into two categories. The first one is called these idealized models. They are usually low-dimensional stochastic ODEs or stochastic PDEs developed by applied mathematicians. While on the other hand, we also have these so-called operational models. They are usually like general circulation models in atmosphere ocean science, or you try to think these are very complicated models, high resolution, containing a lot of features, and are very difficult to run. So these idealized models can accurately characterize certain natural processes. They are often used to understand this larger scale physics, and they can perform time series or coarse-grained spatial temporal predictions. So these are the advantages of these simple idealized models. However, these models only include a subset of variables. You pick up a few key variables and model them, and they are often limited to specific domains. So they are like local models or very large-scale models. On the other hand, these operational models, they are often high resolution and they incorporate many crucial variables. They had a lot of these successful results in the operational forecast. However, bias is always persistent in most of these models, and especially because these models are very complicated, so it's very difficult for them to capture these extreme events and accurately reproduce statistical properties. So we always want to improve these operation models, but the models are very complicated. If you try to change a small part in this model, then very likely everything will be changed, and it's likely the system will blow up, or you can have a lot of additional biases. So directly modifying these models are very difficult. So usually, these are two like separated communities. Like simple models are claimed, at least claimed, to provide guidance for building more complicated models. And simulations from operation models are used to evaluate the performance of simpler models. But beyond these, very obvious connections, these different models are often operate in isolation, and the communication between these different modeling groups or even between these different communities is very limited. So there's a recent paper in this AGU Advances which highlights the importance of these idealized models. It's a short paper, but it listed a lot of advantages of using simpler models to help complicated models. So it's a nice paper to take a look. Okay, so based on this motivation, so we now try to bridge this model hierarchy using the latent space data assimilation. And this work was led by my postdoc Poria Benodaffer and my student Charlotte Moser. So what we are doing is the following. So we have these two sets of models, simple models and operation models. And we also have some so-called reanalysis data, which you can think as observational data, but they are very limited, especially in the atmosphere and ocean science. We only have short observational period. So if we want to use only this observational data to build like a machine learning segregate model, that's almost impossible. So what we try to do is the following. So we have these simple models, and we use these simple models to generate these so-called pseudo observations, which are just like the output from these simple models. Then we build some machine learning surrogate based on these operational model data. And we try to use these surrogate models as a forecast model in data assimilation. Of course, we know they are not perfect because we have a lot of issues in operation models. But since we have this high quality data from the idealized models, these pseudo observations can help us guide the final result. So basically, we try to push the forecasts from the operational models to go to the state of the simple model output, at least for those few variables. Then since those few variables will be corrected, then this entire system will have this improved behavior. We have to use this latent data assimilation scheme because the operation model is high resolution. It will take forever if we run the original model directly. So of course, this latent data assimilation idea is not completely new. There are some existing very nice work on latent data assimilation. However, this standard latent data assimilation method, they just project model forecast and observations to a shared latent space to reduce the cost. But in our situation, because we have these two very separated model hierarchies, our simpler models, compared with a complicated model, we can only have these sparse observations, which means the output in the simpler model only have a few dimensions. A few can mean a few hundred. So therefore, in order to put this specific situation into this latent data assimilation framework, we build this new augmented latent data assimilation. So the goal is to seek a reduced dimension latent space based on the output from the operation models. But at the same time, we also try to maximize the correlation between this latent space representation of the state variable and these sparse pseudo observations from idealized model. So the reason we try to maximize the correlation is we eventually want to do data assimilation. So if we just try to compress the data, then maybe the latent space has nothing to do with the observational physical space. Then data assimilation, at least the likelihood, will not help us. So then this idealized model will not be useful in pushing the forecast towards the right state. So imposing this maximum of the correlation is very important in our framework. And on the other hand, we know we have some limited reanalysis data. We also want to use this kind of information to further correct the forecast biases. And therefore, we use this so-called colloquial learning, and we try to gradually introduce this limited reanalysis data into the training process. So we call the result the bridging model, and this bridging model can efficiently generate many high-quality synthetic data sets which can mimic nature, and they can help us to study extreme events. And they can also provide a training data set for many machine learning tasks, including improving the digital twins. And importantly, because now we incorporate these two sets of models, then we can provide a pathway for enhanced community collaboration. So I will show one important applications to the ocean science here, and we will significantly advance the simulation of the so-called El Niño South Oscillation, or ENSO, which is the most predominant interannual variability in our Earth system. And it has impact of both the global and local weather and climate patterns, as well as a lot of extreme events. So believe it or not, despite these advances in this climate modeling, simulating this El Niño still remains challenges because of its spatial temporal diversity and complexity features. And these features means we have different types of El Niño events. They have different strengths and different lengths of durations. And they have a lot of extreme events. They have multi-year events. So all these features make this entire feature very complicated. So most of the state-of-the-art operational models cannot even generate these two types of El Niño. Two types means we have Central Pacific events and the Eastern Pacific events. But these are like the very basic features. But most of operation models cannot even get these features. And all the operation models have statistical biases, like they are not good at capturing extreme events or some non-Gaussian statistical features. So among all these operation models, the two best operation models are these CESM2 developed by NCAR and this GFDL CM2.5 developed by the Princeton GFDL lab. However, these models still have problems in reproducing many observed features of ANSO, which I'll show next page. So on the other hand, applied mathematicians like us, so we build a lot of simpler models. So we recently built an intermediate coupled model. It's a stochastic model. And this model can capture this ANSO complexity and the non-Gaussian statistics along the equator. So it's like a one-dimensional model just in the x direction. But it can capture all these statistics, very similar to the observations. Of course, the downside is it's a simpler model. We cannot get the features of the equator, and we only contain some of the variables. And some variables like the subsurface temperature from operational models cannot be captured using this model. But at least I want to show like this figure. You can see the first panel is from the reanalysis observation data. This x-axis is location, the longitude, latitude. Then the y-axis is time. You can see these different events. Red means El Nino, blue means La Nina. And you see some extreme events, some events happening in the Central Pacific, some in the Eastern Pacific. And this is a free run of our model. You can see extreme events, La Nina event, some Central Pacific event, some East Pacific event. And you see this probability density function in the two most important regions, the Central Pacific distribution, East Pacific distribution. And the seasonal variation of the variance also can be captured very well. Right? So we also have another even simpler model. We call that conceptual model. It has only 6 dimensions. It's like 6-dimensional stochastic ODEs. So any PhD student, in their first or second year can easily run this model. But this model can also capture these diversity features, at least in the very large scales. So now I want to show the result. Here you see 3 columns. So the left column is the result from this CESM2, one of the best operational model. In the middle, that's Golda's reanalysis data. You can treat that as a reference, the truth, the observations. And the right column is our bridging model result. So the contour, so the shading here is the sea surface temperature, or SST, which is an indicator of the ANSO. The contour is a wind, zonal wind. And in the second row here, the shading is the sea surface height of thermocline, which is H, and the contour is the subsurface temperature. What I show here is variance over time at each longitude, latitude grid point. So this is one of the basic indicator to see, if any model can capture the El Nino features. So, even if you are not familiar with the background, you can tell this first column is very different from the second column. But the third one is pretty close to the first one, right? And remember, our observation, the pseudo observation from the idealized model is only along the equator, and it only contains the SST and H, no zonal wind, no subsurface temperature. But with this latent space data assimilation, we can actually recover all these fields quite well. And we can also get these different El Nino events, which are very similar to nature. We can see the extreme events in the Eastern Pacific, a moderate event in the Eastern Pacific, La Nina, Central Pacific event, and this mixed event. So here we show the statistics, the probability density function. 4 is the Central Pacific region, 3 is the Eastern Pacific, and 3.4 is between Central and Eastern Pacific. But overall, we can see the red curve, which is from our bridging model, is very similar to the blue curve, which is our reanalysis data. This black curve is from CESM, which has a very large bias. And on the right here, we use this 6-dimensional stochastic ODE, and we can correct the SST and the wind biases by a lot. Right now, the variance of SST is located or pushed towards Eastern Pacific. So I also want to mention that this framework can provide us a physics assistant and digital twin framework. So usually we know when we have digital twins, we want to test these what-if scenarios. Basically, we want to say we change the four things, then what will happen to the new scenario. So here, because we have these two models, we can actually do this what-if scenario on the simpler models because we know the entire dynamics. Then we assimilate that to the more complicated models to get this full-field what-if scenario test. And we apply this to this O'Neill. So in the middle column here, it's the current situation. In the left column here, that's the case when we try to decrease the worker circulation. And in the right column, we have this acceleration of worker circulation. Basically, the left column is the past situation, the right column is the future situation. And these are very consistent with people have discovered using their knowledge and some potential observational data. But we can do this very easily just using our idealized model, then we do data assimilation. So, okay, I will move on to the second topic, this conditional Gaussian Koopman network. It's a unified framework for modeling, forecasting, data assimilation, and uncertainty quantification. So eventually, we want to build a stochastic digital twin. So currently, machine learning is a very important and popular tool for data assimilation. And the existing machine learning methods for data assimilation can be broadly grouped into two methods. One is called this end-to-end machine learning method. Basically, you have an input of the state, you have this black box machine learning, you have the output as your posterior distribution, but usually it's just a posterior mean. So of course, this is a very straightforward idea, and it works pretty well in many situations. However, the challenges are very obvious. How to build this map for high-dimensional systems, and how to effectively quantify the uncertainties beyond just posterior mean. And the second method is we still keep this Bayesian framework, but we replace the traditional physics-driven forecast model by a machine learning surrogate forecast model, right? So you don't change this framework, so you can still get the same output as the traditional method, but you can accelerate your calculation in the forecast stage. Of course, the challenges are still in these ensemble methods, right? You still need to do a lot of empirical tunings for localization for the covariance inflation. So what motivates us to build this conditional Gaussian Koopman network is the following. So in contrast to purely machine learning method, we are thinking about maybe we can leverage specific yet general enough stochastic model structures to help us substantially enhance the accuracy and efficiency of nonlinear data assimilation. So in other words, we try not to just use machine learning, but we try to integrate the information of some known stochastic systems into the machine learning framework. So it's kind of like a hybrid strategy with some physical knowledge or mathematical knowledge from stochastic systems and machine learning. So also there's a strong need to develop like a unified framework which can capture the modeling of complex systems, performing accurate forecasts, and conducting efficient data assimilation simultaneously. So we can form this entire loop so we can apply that to digital twins. But meanwhile, we must make sure we can effectively quantify the uncertainties in the state estimation. So if we can do all these things together, then we have a closed loop system. Then we can use this machine-based method to accelerate the forecast and to assimilate the state. So this work was led by a student, Jinlong Wu, and I co-advised, Chen, and my current student, PhD student, Zhongrui Wang. So what we are doing is the following. So let's say we have a set of PDs or stochastic PDs, partial U tutor, partial T equals M U tutor. And let's do a spatial temporal discretization of this system in order to fit into the real world application. So space and time are both discretized. And we use this state U to denote the state spatial temporal discretization. And this G is the discretization of this M. So both M and G are highly nonlinear. And the N and N plus 1 are the current and future time instant. So in many cases, we know the measurements are only partial of the state variables. Just like I said, maybe we can measure the large-scale grid points, but there are a lot of these small scale features we cannot measure directly, right? So that's why it's very natural we try to split these entire state variables into two parts, U1 and U2, and U1 is the observed variable, U2 is the unobserved variables. So correspondingly, we can rewrite this system into two equations. And G1 and G2 are both highly nonlinear just from this G, but we try to write the dynamics of U1 and U2 separately. So this conditional Gaussian Koopman network try to change this entire system to a different stochastic differential equation. So we still keep this U1 variable here, and on the right-hand side, we have this F1, which is a fully nonlinear operator of this U1, and similarly for this G1. But we try to change this U2, we find a nonlinear map, and move that to this variable V here. On the right-hand side, we still have this strong nonlinear dependence of this U1 here and here, but we try to now change the dependence of this V to be a conditionally linear system. So overall, it's still highly nonlinear because U and V can interact. But if we are given the trajectory of this U1, then this V is conditionally linear. And we have some additional stochastic noise here. So F1, F2, G1, and G2, they contain some neural operators in addition to the no physical structures from the original PDs. So you may wonder why we want to do this, right? So I will show the advantages later. But before that, I want to say we have clear mathematical justifications for these conditional Gaussian nonlinear systems. And we had a paper I had a paper with my PhD advisor Andy Maider in 2018. Actually, that's a review paper which is like 100 pages long, and we have maybe 80 to 100 examples showing many of the dynamical systems will fit into this framework or fit into the continuous in time analog. And these examples are Lorentz models, Shear-Water equation, Bosnian equation, Fitz-Honig-Gummel model, SIR, and many ocean atmosphere models. So believe it or not, many of the systems you have used belong to this framework. So that provides us a good physical or mathematical justification of taking this form as our conditional Gaussian Koopman network scheme. So essentially, this CG can transform this general nonlinear system into a highly nonlinear neural differential equations with these conditional Gaussian structures. However, even though we call it conditional linear, conditional Gaussian, the marginal distributions of U1 and U2, as well as the joint distribution of U1 and U2, they are still highly nonlinear and highly non-Gaussian. And the reason is very simple, right? Overall, you treat them as a entire state variable, then on the right-hand side, you see all these nonlinear terms. So we can guarantee we have nonlinear system and the non-Gaussian distributions for every single variable. And that's important because we don't want to just completely do a Gaussian approximation. So we'll miss extreme events. So one of the main reasons we try to rewrite a system into this form is that we can still keep a lot of nonlinear interactions, but this kind of structure will allow us to develop analytical formula for nonlinear data assimilation. And the reason is very simple. We make use of this conditional linear structure, so we can have some closed form to do data assimilation, even though the system itself is highly nonlinear. And when we have closed analytical formula, that means we do not need to use ensemble method. And that's a huge advantage because we can put this data assimilation loss into our training, right? We have a closed form, and we do not need to have all these sampling issues. So we just need to add this additional data assimilation loss into our system so we can train our neural network. Then we can do both a forecast and data assimilation. And when we do data assimilation, we also have the uncertainty quantification. So that part is automatically considered in this framework. So this CG can basically compensate for the structure simplification from fully nonlinear to conditional linear by lifting the dimension of the system from a theoretical viewpoint. And you can think this is motivated by the Koopman theorem, right? Because Koopman theorem says you can always lift a dimension of a system to a linear system for an originally nonlinear system. But I do want to point out one big difference here. So in Koopman, it's eventually it will give you a linear system, but here we still end up with a highly nonlinear system, but just a conditional linear. So we have to say we just borrow some of the ideas there, but our system is very different. from the traditional Koopman theorem. Although we have this high-dimensional system by design, we can always do a dimension reduction using the autoencoder or any other dimension reduction method. So eventually, we have this lifting of the system, then we do this compression. So we try to make this dimension of this V variable still pretty low. So that can help us further to do efficient data assimilation. And finally, I want to point out that even though the conditional distribution of V given this U1 is Gaussian, right? But this conditional distribution is in the latent space. When we project this V back to the physical space U2, we have a nonlinear map. So we are able to have a non-Gaussian distribution of this U2. And this non-Gaussian distribution will be potentially useful for us to quantify a lot of these intermittency and extreme events with these tails. So I want to show a quick, simple example. We deal with this two-dimensional Navier-Stokes equation, and the resolution of the simulation 128 square. So we assume we have 8 times 8 observations. It's regularly distributed in space. So our conditional Gaussian-Koopman network can do both a forecast and data assimilation. We compare our method with 2 sets of methods. One is about this data summation or data assimilation using the standard ensemble Koopman filter with localization, and this very naive method doing interpolation based on the no observations. And on the forecast side, we compare CGKN with DNN, CNN, and the Fourier neural network. In order to make sure it's a fair comparison, we assume the neural networks all have similar number of hyperparameters. So what you can see here on the top is the result of the forecast. So the first row is the truth, second is CGKN. We have similar behavior as this Fourier neural network, and we did much better performance compared with DNN, which kind of diverge, and even CNN, which have different features. While in the second part here, it's a data assimilation result. Top row is the truth, second is CGKN, which is very similar to the truth. ENKF is also very similar to a truth. So if we look at error, basically we have similar errors compared with ENKF. This interpolation didn't work well because you only have sparse observations. But I also want to point out it's not just about the computational accuracy, it's also about the computational efficiency, right? So we compare our data assimilation speed with the ensemble Koopman filter, and we can see we can gain like 600 times, compare with ensemble Koopman filter for Burger's equation, and for the Navier-Stokes equation has 300 faster, compared with the ENKF. And this is very important because when we do the real-time state estimation or sequential state estimation, we do want to make sure we can run these codes very fast. So we have applied this CGKN to many other interesting problems, like we try to recover the deep ocean and the topography, like the seamounts. We also use that to do Lagrange data assimilation based on the Lagrange tracers. We have also done some theoretical studies when we try to incorporate memories, and we have some online learning algorithm to gradually correct its error. So in my last 10-15 minutes, I will talk about this assimilated causal inference method. So what is causal inference? So I'm sure you have heard about this causal inference, these 2 words many, many times. So this causal inference determines cause and effect relationship between variables in complex systems. And it's very fundamental in model identification, policy development and evaluation, as well as decision making. So this causal inference has a huge field, and there are many different methods, but usually you can categorize them into these 2 groups. One is called data-driven method, and the most famous one is this Granger causal inference. Granger won the Nobel Prize a few years ago, and this nonlinear version called transfer entropy. So all these like data-driven or time series methods, they try to discover the causal relationship from time series, and they will provide you this time average relationship. Basically, it will tell you, hey, Y will contribute to Z, X will contribute to Z overall. So it will not tell you at each time instant, X will contribute to Z or Z will reversely contribute to X. There are also some like model-based method. For example, the information transfer, or people use statistical response. So these are very useful methods to incorporate some physics. But the thing is, they can only handle very short range in time. And for most of these methods, you have to compute not just the PDF, the distribution, but the derivative. So that makes the calculation really difficult because you have to make sure you have enough samples or ensembles at the tail so you can take the derivative. And therefore, this method, usually it's very expensive, or it can only deal with low-dimensional systems. So there are a lot of very important issues in causal inference. So one thing is, beyond this time average relationship, we may, care a lot about this so-called instantaneous causal inference, because instantaneous causal inference tells us at each time instant how one variable will affect the other. Maybe X will affect Z for now, but for next time instant, Z will go back to affect X. So we want to look at these dynamic interactions between cause and effect variables, and want to make sure, these are time evolving states. And equally important here to detect the so-called inference range between variables, right? We are not just interested in saying, hey, we want to say X contribute to Z. We want to say how far in future X will affect Z, or how far backwards from Z to X that will be affected. So this time range is important for us to make a lot of policies or prepare for the harmful results. And from a practical viewpoint, we also care about some algorithm which can deal with high-dimensional systems, especially chaotic or turbulent systems. And we want to use maybe only the partial observations because we may not have access to all observations, and want to see how important is this uncertainty in the causal inference. So based on this, I will try to highlight all these topics in the assimilated causal inference framework. So this work was led by my current PhD student, Marius Andrew. So this assimilated causal inference, or ACI, is an inference framework that uses its Bayesian data assimilation to reveal cause and effect relationship. So before I show the detail, I want to mention about some high-level things. So this ACI can identify these dynamical causal interactions, which means we look at each time instant, we can say if one variable affects the other, and maybe at the next time instant, the other variable will affect the current variable. So there are several very important features. One is that we do not require observations of these candidate causes. We only need observations of the effect variables. This is important because, let's say, we want to understand which variable causes fluctuations at the sea surface. So we know there must be some variables in the deep ocean which will, contribute to the surface, but it's unlikely we will have observations of deep ocean, right? We will only have satellite images for the surface. So we do not require this candidate cause to be observed. And because we use data assimilation, so we can accommodate some short data sets. And there are a lot of these very mature data assimilation tools, so our method can be scaled to high dimensions. And importantly, this ACI will provide this online tracking of the causal rules, which may reverse intermittently. And we actually develop a mathematically rigorous criteria for the causal inference range, meaning like in future, how far in future each contribution will have to the effect variables. So in this figure, I try to illustrate the big picture without touching too many mathematical details. So the idea is the following. So we try to run data assimilation in two different setups. So we have this X variable, which is our observation. Y is a potential cause of this X. So first, we use the time series up to the current time instant. We do this filtering to recover the state of this Y. So we get some distribution, right? The observation is kind of noisy, or it is stochastic. Then we have some turbulent model. Then second, we use a time series of X, not just up to the current point, but also up to the future point. Then we do this data assimilation again of this Y at this time t. So we try to compare these two distributions from filtering and from smoothing. So if the information in the smoother distribution is more than the information from filter, that means the future information in X will help us to reduce uncertainty. And reversely, we can say this y will contribute to the future state of this x. So it's more like using the inverse problem viewpoint. And this figure tells us, we want to look at this causal inference range, not just going forward into the future. If we go forward to the future, that's more like a predictability study, which is important. But we can also go backwards. We try to find the attribution of what causes this observed event. So in our paper, we use this so-called relative entropy to measure the difference between filtering and smoothing. So this is one of the most widely used information criteria, but the framework can adjust to other information criteria if we want. So how to compute this causal inference range? It is something pretty tricky. So let's say we denote this capital T as a final time and the little t as a current time instant. So we know our chaotic or turbulent systems usually have only finite effective inference lengths, right? We cannot predict 1 year of the weather from now. So we can actually approximate the actual smoother distribution by using this form. So the actual smoother distribution will conditional on x from 0 to the final time instant capital T. But at a certain point, T prime, we should just stop because using further future information will not help too much. Just as I show in this figure, this is full distribution, right? So it's a full information we can use, but maybe up to here, that's enough. If you use additional information, that will not help you get much better result. So if we use information up to T prime, that is enough, then we basically will take the difference between this T prime epsilon and the current time instant. Then this length, which is the length of this red shading area, that will tell us the causal inference range, right? But you have noticed that this method depending on this threshold, which is very subjective, depending on how we prescribe it. And the issue is that, usually we want to prescribe a small threshold, maybe 10 to the minus 5, but what about 10 to the minus 7? So you can see from this figure, if I prescribe a small threshold like 10 to the minus 5, my causal inference range will be this long. But if I just make a small change to 10 to the minus 7, then the causal inference range can be even longer. And this is highly sensitive, especially when this epsilon is very small. So basically, you have to be very subjective, telling, hey, it will, this effect will, have last for 3 days or 5 days, depending on how I define this epsilon. So it's a very subjective. In order to get an objective CIR, the causal inference range, what we do is we try to look at all the possibility of this epsilon. So theoretically, So we can say, hey, if we choose a large epsilon, then what will be the range? If I choose a small epsilon, what will be the range? So we try to plot this curve, which is a curve that corresponds to the the threshold and all possible range here. And eventually, we do not take any point along this curve, but we try to take the integration of this curve. So if it's hard for you to understand, you can just think about a very simple stochastic model. And we all know we have this so-called autocorrelation function and decorrelation time. Right? Autocorrelation function measures the dependence of 2 points in a stochastic model. And this decorrelation time, which is the integration of the autocorrelation function, gives you just a number to tell, on average, how long this memory will last. So these subjective and objective CIRs can be regarded as an analog of autocorrelation function and decorrelation time. And of course, we do not need to repeatedly compute every single point along this curve, then we do integration. We have designed a much simpler and faster algorithm with some small approximations to efficiently help us to calculate this causal inference range. So I will show a very simple example here. It's a two-dimensional system where this x is what we observe, y is the potential cause of this x. So we only have these two terms in the nonlinear form, but they are very important. You can see this is like a damping term in x. This gamma times y is a stochastic term. We call that stochastic damping because if gamma times y is bigger than this dx, then overall the damping will become positive, so you have exponential increase, right? And this exponential increase will generate some extreme events. But of course, this exponential increase cannot last forever because when x becomes very large, we have this feedback term. which will push y back to a negative value. So that will kill the extreme event. So you can see in this panel A, I have this pink color curve, which is this x time series. You see a few of these extreme events, right? And this blue curve, just look at the curve. So it is a time series of this y. So once y exceeds some threshold and lasts long enough, it will trigger this extreme event. So what I show in this second panel here is this assimilative causal inference matrix. And you can see this just slightly before this extreme event peak, this variable to y2x has the strongest causal inference link here, which makes sense because you trigger these extreme events, right? And only when this y becomes very positive, that will give this strong peak. So it tells you, this y is indeed the triggering effect of this x. Well, here you also see this like a horizontal lines. So they are the causal inference range. So even though at this time instant, the contribution of y to x is the most significant because you can directly see the result. And actually, this y will affect x to trigger this extreme event will happen much earlier. It's not like we have to wait until y becomes a very large value, so x will be the outcome. It starts when y started to grow, right? But it will take some time for this x to adjust to go into the extreme event phase. So this happens much earlier, but this is a good sign because that tells us we can actually find the attribution much earlier for these extreme events. That can help us to do some preparation when we have these damage events happening in nature. So we have another recent paper submitted to some of GUQ. So we study this conditional ACI, which means we may not have just two sets of variables, we have three sets. And we only want to look at the causal relationship between two, but the third set of variables exists. We also studied the predictability and attribution using the forward and backward causal inference range. Here I only show the forward, but we have a backward version. We also look at the tipping point. Now with this method, we can kind of distinguish the bifurcation-driven tipping points and the noise-driven tipping points. We have some applications to the Madden-Julia oscillation, El Nino, and the wind, and we can use this method to identify the minimal reducible models for complex systems. Basically, you kill all the link, which tells you they have very weak dependence. It's kind of a sparse identification method. So, okay, to summarize, so I try to introduce the basic idea of data assimilation. Then I try to cover these three different topics. So we developed this bridging model, which integrates simple and complicated models. We can use this model to efficiently generate a lot of time series or high resolution data, which can be useful for us to build digital twin system. And in this conditional Gaussian Koopman network, we can see we do data assimilation, UQ, and forecast at the same time. So it forms a closed loop. Then this assimilated causal inference will be useful to support both of this bridging model and the digital twin. And we try to understand some mechanism by using the causal inference. So at the end, I want to acknowledge my team. So they are all students and postdocs, which contribute a lot to the work. And especially Chen, he's on the job market. He wrote all the code for the conditional Gaussian Koopman network. He's a very mature research scientist now. And I list all the papers I mentioned in this work. The first is about bridging model. These two are the conditional Gaussian Koopman network, and these are the causal inference papers. So with this, I want to say thank you for listening to my talk, and I look forward to questions. Thank you.
Thanks for the wonderful talk, man.
Thank you.
Let me check. Yeah, there is already one question in the chat room. Please raise your questions in the chat room. So the first question is from Luning, asking, could you talk more details about how to make the augmented latent space in slide 8 for two types of the data and how,
I'll go back. Yeah, that's an excellent question, and thanks for asking this. So we first project our operation model data to this latent space. Then we augment that. So the new latent space is not just about the compressing of data. It has the first part, which is from this autoencoder, but we have a second part, which is our observational state variables from the idealized model. Then when we design this latent space, we use this autoencoder, right? So we have some loss. But we try to also include this maximum of the correlation between these two parts into a loss function. So loss function not just try to minimize the mean square error, but it's a mean square error minimization and the maximization of the correlation. I hope that answers the question.
Yeah. Dylan, did also answer your question about linking and linking. How are these linked together in the latent space? Sorry, I missed that question.
How are these in the latent space?
They are linked together in the latent space, but
yeah. So we do this autoencoder, right? So we build this latent space, but traditional method, you just try to minimize the mean square error between the output and input. So now this is only part of our training loss. So we use this correlation to link these two parts in the latent space.
got it. So while we are waiting for the audience to get us some thoughts, I will jump in to ask some questions, but please bear with me. It seems straightforward. So I want to ask in the CGKN framework. So if I understand correctly, the posterior distribution is forced to be exactly Gaussian. So is it like, do you believe all the nonlinear ODE or PD system would be okay with this assumption, or is there any mathematical limitations?
Very, very good question. Thanks for asking this, because each time I give this talk, people ask this question, kind of similar. So I want to say a few things. So first, the system itself is highly nonlinear and highly non-Gaussian. Only the conditional distribution is Gaussian, not a marginal or joint distribution, right? So if you look at the state variable U1 and V, they themselves are highly non-Gaussian. That's the first point. And the second point is, yes, the conditional distribution of V given this U1 is Gaussian, but remember this V is only in the latent space. When we map this back to the physical space, we have this nonlinear map. So this Gaussian variable will become a non-Gaussian variable. So we can still capture all these extreme events, intermittency, and other non-Gaussian features. Just we try to use a conditional Gaussian structure in the latent space to facilitate data assimilation. But in the latent space, the state variable may not have a clear physical meaning, right? What matters eventually will be the physical variable. So we just try to use this V as a bridge in the latent space just for our computational efficiency. I hope this answers your question.
Yes.
Okay, thank you.
So maybe I can ask one more. So I want to ask a little conceptual understanding about the idea about the what is it called, the idealized models and the bridging model.
Okay.
So yeah, so what I want to ask is maybe I missed it, but is the bridging model forecasting the dynamics significantly faster than the operation models?
Yes. Yeah, I didn't say this, but we try to run our model on this El Nino example, right?
Yeah.
So eventually we run like 40 years because the 40 years is the length of the reanalysis period. So when we have this bridging model, we use only like 8 minutes to get this 40-year data using our laptop. I don't know how long exactly it will take to get this operational model simulation for 40 years, but we cannot run the operational models. It will take very long. It will take maybe a few days. I don't know exactly how long it is, but it must be a few orders bigger than this 8 minutes. And they have this output from their website. So you can download the data. They generate the data for 140, 50 years. So you can use this data, but usually you cannot run these models by yourself because it takes a lot of computational resources.
I see. So you can, with that, you can use the idealized or the conceptual models to get the statistical distribution and compare with the operational models as
Exactly.
well.
So what we need to run as a pseudo observation is completely based on the idealized model. And the idealized are very, very cheap. It's just like a 10-dimensional stochastic PDs. Like 40 years only takes maybe 1 minute or 30 seconds. We can run this very long, right? Then we do this data assimilation. But because we do data assimilation in the latent space, we significantly reduce the dimension. If I remember correctly, our eventual dimension will be like, I think 600 dimensions, and we can capture 99% of the explained variance. So, we rely on this simple model to get the pseudo observations, and we do data assimilation. We can get much longer time series. Then eventually we do data assimilation, we can get much longer spatial temporal patterns. And this long time series or long data set can help us study a lot of the stream events or the statistical behavior.
I see. Yeah, I believe this is a very interesting idea and can be like generalized to different applications. Like what I know from the geologists, they have like conceptual models which are like just the channel loops stacking up very quickly, is simulated in very short time. But in the other end, they also have like the so-called process stratigraphy, where they try to simulate all the sand and mud and loops over years. So I think we have an analogy of using your concept in their applications as well.
Great. Yeah, thank you. I hope this can be very useful to other fields.
Yeah. And we saw one more question from Jiwoo from in the chat room. So could you say a little bit more about the improvement in the ENSO simulation?
Okay.
He's particularly curious if the model was initialized once every couple or a few years.
If the model is initialized, no, actually we just do one initialization, then we run it just forward for many years. So, so the idea is when we do this colloquial learning, it's a method used in the training process. So basically, we use this tool to get a better forecast model using machine learning. But once this model is trained, then we just apply this latent space data assimilation. We just keep running it forward. We start from some arbitrary initial conditions, then we can run it for 200, 400 years. And as long as we have these 200, 400 years data from the idealized model. So there's no restart processing. So all these tricks are applied in the training process. Once the model is trained, they just run it, directly without, doing any additional things.
Hi, Nan. Thank you for the answer. And I think I asked this question because as I know that ENSO is generally known as a kind of boundary condition issue rather than initial condition problem. And then I was interested by looking at this that you have improved this data simulation, which is related to the initial condition, and then ENSO has improved, while the ENSO is more influenced by the boundary condition than the initial condition. So I was wondering that what was the driver of this improvement behind of this.
Right. Yeah. Very good point. So ENSO is limited to this specific regime, right? So if we want to run a physical model or like PD ODs, these boundary conditions are extremely important. But here we just discretize the system into these grid points. So all these important boundary effects have been reflected in the idealized model setup. So as long as we can guarantee these idealized models give us realistic simulations, then we just need to put that as pseudo observations to do the the data simulation. So I guess what you ask more is about how to make sure in the idealized model framework we can have the correct physics to make sure we don't have any incorrectness at the boundary. So that's kind of slightly different from what we are doing here. So we how they make sure when we build these idealized models, these physics at the boundaries are already good enough. Then afterwards, we just need our operation models to follow this idealized model output. So automatically, these boundary conditions are satisfied.
Thank you.